Okay, so what we're going to do today is we are going to put together the couple ideas that we've been working on so far in this chapter. One of them is the whole radians and unit circle deal, and then the other thing that we talked a lot about was the sine and cosine. Okay, and when we talked about sine and cosine, well, let's bless you, focus on the sine function in particular. The sine of an angle was the what?
The y.
The y coordinate, okay? And so if I have my angle drawn right here, what would be the sine of this angle? 0, because the y coordinate is 0. And so what I'm going to do is I'm going to take this arrow, this angle, and I'm going to move it around the circle, okay? And as I do that, I'm going to record the y values that I get as I go around, okay? So to start with, you guys said when this angle is 0, the value of y, or the sine, is also 0, right? Okay? So now if I move this a little bit over this way, what's going to happen? We don't need to know the exact values. We figured out some exact values when this was 30 degrees or 45 degrees or 60 degrees, but hopefully you understand that there's angles in between those also, right? We just didn't use those.
Yes.
What's happening to the y coordinate as this arrow moves up? It's going up, right? And what is it getting closer to? 1. And when it gets to 1 and keeps going here, what does it do now? It goes back down. And so if we were to make a table of those values, what you would see is that the y values are going to go up until they reach a maximum value of 1 right there. Okay? Now we're going to try and think as much as we can in the language of radians. When it hits this maximum value right here, what is the radian measure of this angle? Pi over 2, good, because that's a 90-degree angle. So right there at 1, I'm going to say that this is pi over 2, okay? Then if I continue to go around this circle, what happens to the y values now? It goes down until it gets back to 0 at what angle measure? Pi, good. So this is going to continue to go back down here like this in a nice smooth way until it's 0 again at the radian measure of pi. Do you see what I got going on here so far?
Yeah.
Okay. What happens next? What happens to the y values now when I go here?
Decrease.
Decrease, and they are now negative, okay, until I get down here to y equals negative 1, and that happens at the angle 3 pi over 2. Very good. So it's going to bottom out at the value negative 1. And that's going to happen at 3 pi over 2. I don't have any room either.
And then of course it's going to go back up.
And then we don't even need to play the little circle game here. It's going to come back up until it gets to 0 at what?
2 pi.
2 pi. So when I go back here to 2 pi, it's going to be 0 again. And then if I didn't stop there, but decided for some reason to continue around the circle again, what would the circle, or I'm sorry, what would happen then? It would go up again. It would repeat itself, right?
Right.
So it would look exactly the same as what I have going here. Yes?
So if you were to go to the like 180-degree axis again,
Mm-hmm.
call that
Then I would call that 3 pi, okay? Because I've already gone 2 pi's, and so if I go another pi, then I'll have gone 3 pi, okay? So what kind of a function is this then? Since if I extended the graph, it goes the same up and down and up and down and up and down and up and down. It's a sine function is the name of it, but what type of function is it?
Quadratic.
Nope, not quadratic. What? Periodic. Yes, this is a periodic function, okay? Because it repeats itself over defined periods, right? Okay? How long does it take to complete one cycle of the graph? 2 pi, right? because I have one cycle shown right here.
Yeah.
Okay, so the amount of time that it takes for it to go up, down, and then back up again is 2 pi. What is the amplitude of this function right here? Good, 1, because it goes up to 1, and it goes down to -1, so it's a total distance of 2, and the amplitude is half of that, or 1. Okay? Does that make sense? Okay, so that is the general look of the sine function, okay? So then one thing that we can do with this, if you wanted to, is you could use it to estimate some values of sine that you would not be able to do by looking at the graph or at the unit circle. Because for example, if you wanted to do the sine of 2 radians, we're going to be in radians here for a long ways to go. If you want to do the sine of 2 radians, if you change that into degrees, how would you do that? Multiply by 180 over pi, and that's going to come out to be some weird decimal thing, okay? And the only ones that we were able to figure out exactly were 30 degrees, 45 degrees, 60 degrees, or some multiple of that, okay? So sine of 2 is not something we can come up with. But you could look at this graph and use the graph to estimate it instead. So as I move my pen across the x-axis, tell me when to stop when I get to about 2.
I don't know.
Where's 2?
Right where you keep going.
Already went past it? What's pi over 2? About 1.5, a little bit more than 1.5. Pi is 3, right? So it's going to be somewhere in between and maybe this right here. Okay? So what would you estimate the value of the sine of 2 to be? 0.8-ish? Okay? Anybody else want to give that a try?
Yeah, sounds good.
You're going with 0.8-ish? You want a higher one? 0.9?
0.732.
Okay? Let's figure out what the actual retail value is. So when we're doing this, you guys need to make sure on your calculators that we're in radian mode.
Where are we at?
Okay, so hit the mode button, go to radians, and we're estimating the sine of 2, and the answer is 0.9. So it is a little bit closer to 1 than you thought.
So you wanted the radians to be dark?
Yeah, you have to highlight the radians.
Mine was
already
Okay, right, should already probably be in
Okay, now what?
What? Oh, I just did sine of 2. Okay?
0.9.
So 0.909, so 0.9 was a pretty good estimate using this graph, okay? How about an easy one? What would the sine of pi be from looking at the graph?
1.
Nope.
0.
It would be 0, because if I go over to pi on
That
the
is an easy
x-axis,
one.
then I don't have to go up at all to get to the graph, so the sine of pi is 0. Okay? How about estimate the sine of 3?
0.1.
What's that? About 4?
0.1.
Okay, well, what's the maximum answer you can get?
1.
1. Okay, 0.4. Where's 3? 3.14, so it's right about there. Okay, so it's going to be a pretty small decimal, right?
Maybe put 1 for it.
So sine of 3 is about 0.14. Okay. So do you see how the numbers that the calculator is throwing at us relate to the values on the graph? Yes? Okay. All right, so let's talk about these guys here a little bit. So let's get a good sine graph going on your calculator. So clear out anything that you have in there already. And I would like you to hit your window button. And since we're doing radians, we want to use things that make more sense. So instead of going from -10 to 10, I'm going to go from 0 to, how long did it take to complete one cycle?
1.
2 pi. So let's make our x maximum be 2 pi. Okay? And then for my scale, instead of going by 1s, let's go by pi over 2s. Because that's how I... What?
Do you need to put that in parentheses?
How'd you do
Nope.
over 2 divided?
Divide by 2. Okay? And what was the maximum or minimum that I could have on my
1
graph?
and negative 1.
1 and negative 1. So I'm going to go a little bit past that. So I'm going to go negative 1.5 and 1.5 so I can at least see the top and the bottom. Okay? So now if you have y equals,
Wait,
that's because you put your y minimum
the
in
y
as
scale?
1.5 and you put your y maximum in as negative 1.5 and your minimum can't be bigger than your maximum.
What's the y scale?
I went by 1 this time. Okay? And so there's the graph that we just came up with, right? The sine of x.
Mine was the opposite.
Okay. I just typed in y equals sine of x and graphed it.
I like it.
Okay? What happens? We get to play this game again that we played quite a few times. Yes? Did you hit graph? Are you rating?
Did you like sine?
Did you type in y equals sine of x? You did everything correct, but your calculator messed up.
Ooh.
Oh, your y minimum each, I see.
I got it, Katie.
Mine says error.
Oh, I got
Straight
that.
flat line.
That's why I'm not.
Two flat lines.
Yeah, but I did it on the same.
I don't know, I think it's like a parentheses.
Because your y minimum and your y maximum are the same. They're both negative
Well,
1.5.
there's mine flat line.
It's not going to work. You have a bad scale.
You're dead.
You, my dear, did not use the weekends like you were supposed to.
Yeah, I don't think I.
Okay, so here is the graph of the sine function, which we looked at before. What we're going to try and do now is we're going to try and figure out how, if I change this function, how does it affect the graph. So to start with, let's take a look at the graph of y equals sine of 4x. Okay? Any guesses how that's going to change the graph?
They're gonna go
Down.
You think it's going to spread it out a little bit more?
Yeah.
Okay. You think what?
close.
It's going to make it closer.
Probably closer
Okay,
together.
if you look at the graph, what that does is it has squished it so that it's closer together. Okay, here's the key. How many cycles of y equals sine of 4x are on the screen? 4. Okay, so when I put a 4 in there, that means instead of showing only one cycle between 0 and 2 pi, it's going to show me 4 cycles between 0 and 2 pi. So if you want to do the cool thing and make the little heartbeat graph, instead of putting 4x, okay, let's put 200x. Okay, and really tweak things out. So there's the regular one, no big deal. And now the calculator has to fit in 200. Doesn't seem like that's going to be 200. Yeah, I must have did something wrong. That's not 200.
Yeah, mine's not gonna be 200 either.
Okay, it must not have the resolution to show that, but you can cram in a bunch of different things, okay? Anyway, so let's go back to the normal one that we did that was 4x. If you zoom out, you can see it? Okay. So let's go back to y equals sine of 4x. What is the period then of this new function? The period of my original sine function was 2 pi, right? Now, how many cycles did I fit in the distance between 0 and 2 pi? 4. Not 8 pi. You multiply, you want to go the other way around. The original period was 2 pi, but now I fit in 4 cycles in that distance. So I have to divide by 4. Okay? So pi over 2. And so if you look at your calculator, you should be able to see that that's true. We made our scale go by pi over 2, so I fit one complete cycle in there from the distance from 0 to pi over 2. Okay? So what would my period be if I graph y equals sine of 8x? Pi over 4, right, because I take the original period, which is 2 pi. Now I'm going to cram 8 cycles in there in that same distance, and so that reduces to pi over 4. Does that make sense?
Yeah.
Okay, so you understand how that goes? What? Okay, and then the last thing we're going to do, and I'm not going to give you an assignment today because we're almost out of time. So I'll give you an assignment tomorrow. You can work on it all during class tomorrow. What happens if instead of putting a number inside the parentheses, I put a number in front of the whole
It's gonna
thing?
make it longer.
It's going to make it, okay, so I'm going to go
It's gonna change the
4.
amplitude.
It's going to change the amplitude, yeah. So we'll go 4 sine of x here. So there's my original one.
Look at the fancy.
Now I'm going to go 4 sine of x, and now we can't see the top and the bottom because it went all the way up to 4 and all the way down to -4,
But
right?
it's still only one period.
Okay, but it is still only one period. Why?
Because we didn't change it.
Because it's just plain old x. Yeah, I didn't change that part, I just changed the amplitude. Good. What would happen if I tucked the negative sign in there?
Well, with the
Well,
thing gets
flip
smaller.
flop it.
Well, now.
It would what?
Flip-flop.
Yes, it would flip-flop it over what? The x-axis. And so that means that instead of going up to start with,
Go down.
this one means flip-flopped over the x-axis, so it's going to go down to start with instead, okay? So all the rules that we've talked about in terms of transforming functions hold true also for the sine function as well, okay?
Gotcha.
All right, good deal.